Morning, everybody. Wow, you guys came in with energy today. I like it. Is there something going on? We're just all awake? Woohoo! Not me, Mr. Balogh. I'm not awake. That green is terrible on that screen, isn't it? Okay. This is the kind of thing you need to tell me. It looks great on my iPad screen, right? But up there with the poor bulb and all that kind of stuff, you just need to let me know that kind of stuff. So I'll try to avoid using that green. See if I can't find a different color to use. And we'll do that moving forward. Here's the roll sheet. We'll set this one around. I managed to get everybody. I think I missed 2 names out of the ones that I tried. So solid 90%. Like 20. Something like that. So anyway, you have homework due Monday, right? No, it's Labor Day, right? Is it still due on Monday? It is due on Monday? Yeah. You want to do on Tuesday? Yes. Okay, but watch out for chapter 20, whatever, 3? Okay. I honestly don't know the numbers of the chapters. I know the topics. I know the first one was Coulomb's law, and the second one was electric field, and the third one's Gauss's law. But I just don't associate the numbers very well with it. Okay, so I'm going to write this one down. It's important. Change due date. Due date. Okay, remind me when I'm done here. All right. So I will change the due date so it's not on Labor Day, right? Because technically a holiday, although we all know students don't get holidays. All right. Ooh, that's right. We were doing this. What was this? Finding the electric field at the center of an arbitrary arc. Take a line of charge, take a wire, bend it around. It could be it could be half of a circle, it could be a quarter, it could be an eighth, it could be whatever, right? We're going to find the electric field right there at the center. I got to the point where I would manage to write down my differential electric field. In other words, my little contributions to the electric field that I'm going to find by integrating. But we ran out of time to do the R vector. So let's see if we can't whip out some sort of R vector. I need like a different color. None of these are good. I'll figure that out later. Is this one too faint still? Yeah, no good. You just don't like it. Fair, I guess. Is that one too faint? That's gray. I do have a purple, but I've already selected it. I'm trying to find like a 5th color. Anyway, it doesn't matter. Okay, so we'll go purple. My R vector, right? This vector that's pointing, starting at my little piece of, my little chunk, right? And heading down to the origin. How do I write down that R vector in like terms of things that I know? So, could we write it down in terms of x and y? It's like a negative x I hat, negative y j hat, right? The problem is that we are not integrating in x or y, are we? What are we integrating in there over there in that horrible green that you can't read? D theta, right? So we know we want our R vector to be given to us in some like function of theta. I think I heard it over here, right? It's like sines and cosines. How do we like find sines and cosines of this thing? We've got a vector points down like this, right? And we have an angle, quite frankly, that it seems to be in the wrong place, doesn't it? Got that angle right there. But is that angle replicated somewhere else? there, isn't it? Alternate interior angles. Okay. Doesn't matter which one I actually draw because the x component ends up touching that angle no matter what, right? So what will the x component of this r vector be? It will be r cosine theta. It's touching, right? The hypotenuse is r. It's the side I'm looking for is touching the angle. That's the magnitude. And what's the direction? Negative I hat. Oh, wait a second, Mr. Balogh. Why are you doing x and y but doing angles? Well, you can do that. I mean, I could solve this whole problem, I guess, in polar coordinates, right? But that actually turns out to be a lot more difficult. Plus, what are they talking about out there? What's the magnitude of the y component? R sine theta. And what direction does it point? Negative j hat. So there is my r vector, right? What is the magnitude of my r vector? Don't write this down. Technically, it is r cosine theta squared, all that squared, plus r sine theta squared. But we're way overthinking this. What's the length of my r vector? R. Cosine squared theta plus sine squared theta is 1. And what's r squared plus r squared? 2r? Well, I factor it out, so I don't have to add it together, right? Okay. And I have cosine and then what's the square root of r squared? R. Duh. It's r long, right? My magnitude of r is r. Okay, which is handy because that's kind of how I've got it written over here, right? So now I've got my r vector written in terms of things I'm integrating against. So that makes my differential electric field thing right here equal to k lambda r d theta all over r cubed. That doesn't change because the magnitude of r is r times r vector, which is negative r cosine theta I hat plus, minus r sine theta j hat. All right, where does that differential electric field go? Straight into my equation. So now what have I got? I've got the electric field is equal to the integral between the two angles that I have specified, theta 1 and theta 2, as measured from the positive x-axis, of k lambda r. Can we get rid of one of these r's right now? I've been carrying it around for a while. I don't need to, right? Because it cancels out one of those, doesn't it? Oh, there's another one that gets canceled out. Can I factor an r out of here and then cancel it again? Yes. So let's clean that up. K lambda over, oops, wrong color. Over r d theta survives. And then I have negative cosine theta I hat minus sine theta j hat. So this, and by the way, what is a constant in this integral? K is a constant. Lambda could be a constant unless they tell us that lambda changes with r. Fine. What about r? Yeah, it's also a constant, right? So all those things can come out. So this thing right here, not completing the integral because I kind of have an arbitrary set of angles. And my integral, I'll work out my integral slightly differently depending on the angles that I have. But everything in that box right there is the solution for any arc of charge. I'll do a specific example right now. But I just want to point out that given a quarter of a circle, given half of a circle, given 3/4 of a circle, boom, right? You can just put the angles in there for whatever situation you have been given. So that being the case, knowing that we have this equation, and it's the general solution, or at least the general setup of an arc of charge. Let me add a page here. We'll do that one. And then paste it. There we go. All right. So there's the general solution for an arbitrary arc of charge, right? Let's do the example where we do a semicircle. Like an arc of charge that goes like that. So where does this arc of charge start? 0 degrees. And where does it end? 180 degrees. Okay? Before we even jump into the integral, what can we figure out about the electric field right here at the origin? Can you take a guess if this is positively charged, uniform positive charge? You want to take a wild guess as to which way the electric field points right there? It's straight down, isn't it? Because any electric field vector from this side is going to get canceled by one from that side in the horizontal direction. And what's going to happen to the verticals? They're going to add together, right? In terms of my solution up here, what does that mean I can assume about all the x components? They're going to cancel out. Mathematicians would be like, prove it. Physicists would be, no, you prove it. Can't put the burden on us. Make the mathematicians do it. So, our argument is going to be by symmetry. Okay, all of the x components will add up to 0. So that means that the electric field at the origin here is going to be k lambda over r, integral from 0 to 180 degrees of negative sine theta d theta j hat. Okay, we'll go with that. Now, I put degrees in. I probably should have been a little bit better and put radians in. Because radians will be in units that will agree with all the SI units of everything else that's in that problem. So we'll go with the radians, especially since we know kind of what sine and cosine of like 0 and pi over 2 and stuff are. Okay, so what is the integral of sine theta? D theta? Is it negative cosine?
Yes. Negative cosine.
It's negative cosine, isn't it? So that's a little bit worrying because now we become positive, right? So it's like the negative sign comes out, k lambda over r, and then I have a negative cosine evaluated from 0 to pi. So that and that cancel each other out. And now I've got k lambda over r. Okay, what's the cosine of pi? Oh, there we go. Got my negative. Why was I worried? Which way do I know this has to point if this is a positive charge? It's got to point down, right? So I knew I needed a negative j. Oh, there's a j hat floating around. Negative 1 minus, and then what's the cosine of 0? 1. Oh, what's negative 1, negative 1? Why is there a factor of 2 in here? There's 2 contributions to this electric field along the y-axis, right? I like that the factor of 2 showed up. So what am I left with? 2k lambda over r negative, it was a negative, with a negative j hat, right? So there's my electric field at the origin from that thing. I could, I guess, like, if we know that we just dump charge on this and it's totally uniform, that could be q over the length, right? What's the length? How long is this arc? It's pi long. Okay, so you can put pi in there. It's pi times r. It's the arc length, right? We need a length in there, so it would be the angle times the radius. So yes, both of you are right, right? And then we could throw that in there, and our electric field at the origin 2k q over pi r squared j hat with a negative sign. And there we go. That's the equation for a semicircular arc. I'm going to go ahead and change this. Brandon, would you mind closing the door? All right. What if the arc were, like in your homework, only 90 degrees of arc? Going from, say, the vertical to the horizontal, like from the y-axis down to the negative x-axis. Just kind of back up to that integral, right? Now, do you have to do both the x and the y directions now? Yeah, you would. Okay, because there isn't a symmetry argument where that's going to cancel. Then he gave you another homework problem where, like, the polarity of the signs flip between two quadrants, right? You can recycle, like if you can generically find out what a quarter circle is, you can just keep recycling that result over and over again, flip the signs on the charge, and away you go, right? So it's pretty handy. The thing up there in the box is pretty handy for any amount of circle. And I would solve, we've done it for the semicircle, I'd solve it for the quarter circle, and then you pretty much have every answer you need to do anything we'll throw at you. Kind of nice. All right. I keep forgetting to mention this because it's just so present in my life. I put a PDF. Did I talk to you guys about this? Yes. Put a PDF on. I did talk about this? No. I put a PDF on the Unit 1 module. Okay. What does it mean to integrate by Dr. Ross Spencer? Dr. Ross Spencer was one of my teachers and advisors way back in the age of the dinosaurs. This is the textbook, the document I've been operating off of as I've been teaching you how to integrate. Okay? Now, it does contain some, like, sample problems to try. You don't need to do those, okay? All the answers are in there. But it does go through all the different geometries of slicing up things like cylinders, okay? And you know, different ways to do it, and different ways to do spheres and things like that, okay? Some of the pictures you'll notice from it. I gave you a copy of that document. I've never seen a clearer explanation in any textbook anywhere of the connection between what it means to integrate something, literally to add up pieces of things, right? And how that corresponds to the different geometries we take advantage of in Physics 4B. So that's there for you. You're not required to read it, but if you wanted something to refer to other than my messy handwriting, Dr. Spencer put together that many moons ago, and it still pays dividends. It's fantastic. All right, we are done with chapter, whatever that was, 22. And now it's time to go to Gauss's law. The good news, I think, is that it's almost over. This first unit is coming to a close. Okay? You've learned about Coulomb's law. You've learned about electric fields. You have remembered things about vectors that you wish you could have stayed forgotten. You've learned new ways of thinking about mathematics and integrals, and you're probably drowning, going, I can't do this. You can do it. It's a matter of practice, really working, not letting it beat you. Okay? but you just keep plugging at it, and it's going to start coming together. Hopefully that all comes together before a week from this Tuesday. Because what happens a week from this Tuesday? The exam, right? So that means we have what's left of today, and not Monday, but next Wednesday, to talk about Gauss's law and start getting you ready for that exam. We are going to review a Monday from Labor Day. We're going to have a review day in here. Review means you come to me with questions. I've been giving you questions for 3 weeks, okay? Giving you homework, giving you all these things, right? I'm not going to give you additional review materials, okay? You need to come to me with questions, clarifications, all that kind of stuff. Next Wednesday, we'll talk a little bit more about like sort of the exam, what to expect, try to settle your minds a little bit of what the exam's going to be about. But we'll get there, okay? But let's do this last hurrah when it comes to. We're not leaving electric fields behind, but in the next unit, we are going to take a step in removing all of the vectors from this stuff, okay? And you, Mr. Balogh, why didn't you start there? Well, you'll see. Gauss's law, in general, is an approach that lets you avoid doing integrals. That's what it boils down to, and I'll explain what that means in a second. But what I have to do is I have to teach you about flux first. Gauss's law is a, dare I say, mathematical idea that really helps when it comes to figuring out very complicated forms and distributions of charge, okay? Now, as soon as I say the word flux, this always comes up, okay? Please tell me you've seen this movie. Yeah. Or series. Okay, good. They're old, right? Marty McFly from the 1980s went to the future. That was 2015 in the movie. I still don't have self-tying laces or hoverboards. Nike tried the self-tying laces thing. It didn't work. Hoverboards, they work. It's just you need a lot of liquid nitrogen. So anyway, what's that thing down there in the bottom? The flux capacitor. And in the movies, what did the flux capacitor enable? Time travel, right? Now, when the writers sat down to sort of come up with this idea, this turned out to be an Easter egg for people that knew what flux was. The flux capacitor is an oxymoron. Does anybody know what an oxymoron is? It's like when you put two words together that have opposite meanings. Jumbo shrimp. Government efficiency. Right? So, why is it an oxymoron? Flux is all about flow. It's all about how much of one thing moves through another. Okay? I'm being very general there. The flux capacitor, what do capacitors do? They store things, right? So this flux capacitor is supposed to be storing that which passes through. It's a big Easter egg for nerds, right? You hear it and you go, oh, I see what you're doing there. Very clever. Steven Spielberg and Robert Zemeckis. Okay, flux. Why are we talking about flux? We're going to need to understand flux to be able to employ Gauss's law. So we got to talk about what it is. And kind of one of my favorite analogies when we're talking about flux is to think about flowing water. Okay, so how would I measure flux and do all that kind of stuff? So we've got a stream here in the woods. Okay. And let's say that we are going to try to, catch some fish. Or let's say that you've got a net, or maybe even better, a piece of like chain link fence, the fence that's got the squares in it, right, all over, okay? And I ask you, I was like, okay, I want you to go stand in that creek, and I want you to put the fence in it so that you get the most water flowing through the plane of the fence. How would you orient the fence? Like if the river's flowing from that side of the room to this side of the room, How would you stand?
Perpendicular to the flow.
Like the plane, like the flow's going that way, right? And the plane of the fence, right, would be oriented, like you said, kind of perpendicular, right? So we get the most amount of water hitting the surface of that fence, right? Flux would measure how much water flows through your area per time. Or even, not even per time, okay? It can just be the amount of water that's flowing through your area. What happens if we change the size of your piece of fence? Does the flux increase and decrease? Sure, right? But even more, if we change the orientation, if I hold the fence like this, well, now how much water is flowing through the face? None, right? Okay? What happens if I take the fence and I hold it over my head like this and I go down in the water? Still none, right? So do you see how orientation of this surface matters? Okay, now I give you a mesh box, like a cage or something like that. It's still, water can flow through it, right? But I give you this mesh box in the shape of a cube, and we plunk it down in the stream. What's your guess as to what the net flux is through that cube? Is it double? Now, of the cube, how many faces actually have flux? Just two, right? The front and the back face. But what's different about those faces? For one of them, the flux is flowing into the cube. And then the water then on the other side flows out. So it's zero flux. You're like, okay, wait a second. That's kind of okay, Mr. Bale. I'm a little bit lost on that one. But it gets worse. And it comes back to the orientation of that surface with respect to the water. Flux turns out to be a scalar quantity. Kind of nice, right? But how do you get a scalar from a vector? Because the flow of the water is a vector, has direction, right? And something else. What does the other thing have to be if we were going to add, multiply, divide, whatever we're going to do to a vector? How do you get a scalar out of a vector and something else? What does something else have to be? Has to be a vector, right? The dot product between two vectors gives you a scalar quantity. Flux. Make sure I'm going to write this down the same way your book does. Okay. Flux and can I just apologize before I do this? Okay. To the great violence that is going to happen to a concept that you thought you knew about. Like you thought you had this one nailed. You haven't worried about this idea in a long time. Okay? At least in terms of like your knowledge of it. Flux. And now we're gonna flip. We're gonna say electric flux. Because we could do water flux, we could do gravitational flux. We're gonna talk about electric field flux. So instead of a river, it's gonna be an electric field. And is electric field a vector? Yeah, right? The electric flux is the dot product between the electric field and the area of the surface that you put in the electric field. You're too stunned to raise your hand. What's wrong? Areas of... What's area? What's the area of this tabletop? This side times that side. I'm done, Mr. It's a scalar, Mr. Balogh. Right? Please tell me it's a scalar. Area is a vector. Anybody need tissue? Have you ever been taught that area is a vector? Probably not. But it is. Let me see if I can help you understand why area could be a vector. I'll use my physics 4A binder to illustrate. Okay? Does this side of my binder have an area? Yeah. And is this area different? Yes. What's different about it? Its orientation in space, right? If I show you the amount of area like this, but then I tilt my binder, do you see less area, like effective area? Like here, you saw the whole height, but as I shrink it, right? Okay, and indeed, if I turned it like this, some of you are now seeing the area more directly, and some of you are seeing it less, right? Area has a vector direction. For a plane like this, that direction is perpendicular to the surface. So my area is oriented like this, but if I turn it up, it now has this orientation. Did the magnitude of my area change? No. But did the orientation of my area change? Yes. Absolutely. And orientations of areas now matter. Can we go back to when I was innocent? I didn't know that piece of information? No! We can't. Because this is powerful. This is really, really powerful. And how is this really, really powerful? Electric flux. We have an electric field moving across the room like this, right? And if I take a surface, say a square, right? And I orient my area vector, pointing out like this, right? And the electric field's going from left to right, and I turn and I orient my area vector left to right, then that flux becomes the biggest it's ever going to be, right? When two vectors point in the same direction, I get the most thing, right? What happens if I turn around? It's negative the same number. 180 degree difference between these two, right? Okay. But what happens if I make the area vector perpendicular to the electric field? I get 0. And in the case of the cube, all the surfaces that have area vectors perpendicular to the electric field end up being 0. But the one oriented with the flow becomes positive EA, and the side oriented against the flow is negative EA, and when you add up all those sides, what do you get? 0. It captures it perfectly. Flux captures the essence of an idea. How much of a field is moving through some arbitrary, imaginary surface. The surfaces in flux are always figments of our imagination. But if I wanted to find, say, the electric field around the dome of the Van de Graaff generator, we know there's electric field there, right? Is it possible for me to construct a surface in my imagination around the dome of that Van de Graaff generator that captures all of the electric field coming off of that Van de Graaff? It would kind of look spherical, wouldn't it? Well, I could put a box around it, I suppose, right? But what we're going to want to do is take advantages of flow symmetry. I'll talk about what that means in a second. But a very loose or generic overarching definition of flux would be the dot product between whatever electric field vector we have and whatever area we have going through it. Now, this of course assumes that like everything's like perfectly uniform, okay? If our electric field changed in space, if our surface area arced or changed its shape or something like that, what we would have to do is break that area up into little tiny areas, find the flux at every single one of those little tiny areas, and then do what to find the total? The integral over a closed surface of the electric field dotted into a differential area.
What integral symbol did I just put on? It's not an infinity symbol.
What does the circle in the middle of that integral mean? It's a closed integral. In this case, it's closed over an area. In math, they probably, if you ever countered, did they do this? No? You'll see it eventually. They'll do that usually in math to integrate that it's a two-dimensional integral over an area. Okay? In physics, we're like, no, you just do one integral. Right? We do stupid math tricks to make sure we only ever do one. Right? But what that notation there is that we are going to calculate these fluxes, this electric flux, by assuming closed surfaces. I know I started with the example of like a chain link fence. That would be kind of like an open surface or a surface that ends in space. What I wanted are boxes, okay, closed boxes. I want basketballs, closed spheres. I want closed cylinders, okay? I need to know the surface area of whatever shape I've got, but I need to make sure that that surface completely encloses the thing I'm trying to figure out the electric field of. If I want to know the electric field of the Van der Graaf generator, enclose the Van der Graaf generator. I want to know the electric field around a car that's been struck by a lightning bolt, wrap it around, right, the car. If I want to know the electric field of a flat plane, I'll do a box. Okay? So we're going to take advantage of symmetries to avoid having to do some really nasty math. And I know right now you're a little bit panicked. You're like, oh my gosh, not another integral. This is where Gauss's law comes in. We talked about one half of Gauss's law, which is this mathematical concept of flux. Okay, so let's now talk about. This is a horrible picture. Oh. Notice they're calling this kind of weirdly heart-shaped blob, right, a Gaussian surface. It's like an arbitrary shape, and then they've got this electric field. The reason I wanted to show you this picture is because to show you the horror of what could possibly be and then save you from it, I will appear like a hero. Right? See how they've taken that surface and broken it into a bunch of little squares? And at each square, they're finding the angle between the orientation of the area and the electric field at that point. And then they do dot product, right? And then you integrate all over that thing. In practice, this is horrible. I've done it. Okay, I've done Gauss's law in all of its horrible, nauseating detail. Okay, what we're going to do, okay, is be very clever about how we set up and approach these things. And what does Gauss's law tell us? This is Johann Friedrich Gauss, John Fred to his friends. Absolute pedal to the metal genius. Like the kind of like brain. I don't know if you've heard stories about like some people who you can give them like what day of the week was it at 896 AD, right? On this date, and it was Thursday, and they'll be right. Or you give them like really long like multiplication to do, and they can tell you that fast what the answer is. Okay. Yeah, they're sometimes called savants. Okay. Or people that have never like seen a piano before, and they just hear a piano song and they sit down and they can just play it. Just incredible, like amazing levels of intelligence. But often those kinds of people have deficiencies in other areas, usually social things like that. Gauss was no different. Okay, he was married. He had kids. Must have been an interesting marriage. He this is very sad. Missed his wife's death. She was poorly. She was ill. The servants came up to tell him that you better come down here, master, because your wife's on her deathbed. He's like, yeah, I'll be there, and he totally forgot. So like, kind of didn't click in terms of tying his shoes, but holy cow, did that mind produce mathematics that we're still like taking advantage of today. Down in the lower corner, he came up with like the mathematics of geodesics, which laid the groundwork for latitude and longitude and all the way we do modern navigation, including GPS. Like, he had the math down in the 16th century for GPS that we couldn't even launch. I know many of you have seen this curve in some way, shape, or form. You've either been tested against it or each other, right? But this is the Gaussian bell curve, named after this guy, okay, in statistics. He did differential geometries that would lay the foundations for being able to do geodesics in space-time for Einstein's theory of relativity. That's some sort of logic triangle. I'm not even going to pretend to understand, right? Like, prolific. Just a prolific mathematician, okay? And we are only telling you about one of the things that he came up with. And it is so astoundingly simple, if I can use that word, that I'm going to struggle for the rest of the day to prove to you that it actually works. You're going to look at what I'm about to tell you, and you're going to think, this can't work. It works. I've done it a lot. It just works. What is Gauss's law? Gauss's law states that the electric flux through any closed surface is equal to a constant. And that constant is the amount of charge that's enclosed by a Gaussian surface divided by epsilon naught. What has Gauss just told us?
Yeah.
That's Q enclosed. That integral is supposed to turn into what? A number. Right? And what does that number depend on? A charge. Divided by something that never changes. I once had an instructor tell me, I was sitting there, I was looking at this the way you're looking at it, going, I don't get it. Like, I don't understand what the big deal is. I'm not even gonna pretend to understand what the left-hand side says. But I can't even picture what that is, right? The right-hand side, I'm okay, like it's a charge divided by a number, okay, fine. But why, teacher, are you so revved? He was really revved up about this. And here, I was like, I don't understand. Can you explain it to me a different way? And he just looked at me and said, and I will never forget this, Gauss's law is where you don't do the integral you do see, and you do the integral you don't see. I said do. I didn't understand what that meant either. I was like, I don't get that one either. Is there an integral that you see? Is there an integral on the screen? Well, guess what? We're never going to do that integral. Why are we never going to do that integral? Because of Gauss's law. Because we have a statement that that integral has to equal the stuff on the right-hand side, which doesn't have an integral in it, right? So where's the integral we don't see? It's on the right-hand side. And you've already done it because I made you do it in the very first chapter, even though it wasn't in the book. Where's the integral we don't see? Hint, it's not epsilon naught. It's charge. Do you remember how I introduced this concept of integration to you about how to find the total charge on something by breaking it up into strips, into cake layers, into chunks of a rod or something like that, right? I laid the groundwork for this moment. Gauss's law is not doing the integral you do see. We're not going to do that integral. And I'm going to add, but sometimes having to do an integral that you don't see. That sometimes is that Q. Sometimes we don't need to integrate to find Q. Sometimes we're just given Q and we just run with it, right? But they could give us a situation where we have to find Q by integration. So we might have to pull out that tool and use it. But doing charge integrals is way better than doing that, right? Over there on the left-hand side. So what I want to do from here on out is really just do examples, okay? Show you some videos, do some examples, okay, of using Gauss's law. I've come to understand and know when I was in college that Gauss's law, for all of its mathematical formalism, these sort of like, I'm inventing a surface and it doesn't exist and it's kind of this weird idea and it seems very arbitrary. I don't generally do well with sort of abstract mathematics like that. I discovered that this was a total end run around mathematics. This is how you do integrals without having to do integrals. And it actually turned from something I hated, absolutely hated. I hated 4B. Hated it. And vectors, we said integrals, and Gauss's law. It gets worse. Hated it. Couldn't get out of the class fast enough. Just wanted to go on with my physics career, was never going to have to deal with electricity and magnetism again. Boy, was I wrong. Came to fall in love with physics 4B in my senior E&M class and then later in my graduate school class for a reason that I'll probably tell you here in a few minutes. Let's do point charge. Let's do video. Let's do video. Let's give you some more conceptual pictures to kind of wrap your brain around here. And of course, like any good showman, I forgot to load the videos ahead of time. Here we go. Let's do that. Let's get that one away. What do you think the chances are that the new building is going to have a light switch right next to where I actually have to push the play button? 0. Like, why is there not a light switch right?
Gauss's law states that for any closed surface, the total flux is proportional to the net electric charge inside.
There's the electric field coming out.
If there's no net charge inside a surface, any positive flux
Positive and
outward
negative charges, right?
through it
Flux comes out.
must be balanced by an equal amount of
What is
inward
it gonna do?
or negative flux.
It's going to go right back in. So zero charge enclosed, zero electric flux. Right? Now, be very careful. Does zero electric flux mean there's no electric field? No. That's not what it means at all, right? It just means that whatever charge is enclosed by our surface has to be zero. So if there's positive 10 in there, I know there's negative 10 in there also. Somewhere, some way, some shape, okay? But that's what that means, okay? The power of this is amazing.
An extended region of charge might consist of many point charges in space.
Van de Graaff generator dome.
But if it's symmetrical, the electric field has only one place to go, and that's outward. According to Gauss's law, the flux through a closed surface outside depends only on the total charge. And if the charged region is a sphere, the size makes no difference.
So, in other words, the electric field outside is the same, whether the charge is uniformly distributed in a sphere or concentrated at a point at the center.
Huh? The size of the charged sphere doesn't make any difference? Why? It was symmetrical and the amount of charge. Is there anything in Gauss's law on that right-hand side that says, it depends on how the charge is arranged? Does it depend on what the charge's favorite color is? No. What's the only thing it depends on? The amount of charge that's enclosed by this imaginary green balloon thingy, right? What we call a Gaussian surface, right? And, mind-blowingly, we can go inside those charged surfaces, those charged objects. And the only thing that matters is what's inside our Gaussian surface.
What about like the square? Would it still matter?
We're going there. We're going there. Don't. We're going. Okay. So let's do the electric field of a point charge. Where did my? Here we go. Hold on. Disconnect. Nope. It says it's still going. My iPad window is gone. Where'd it go? Nope. Nope. All right. We'll do this. When in doubt, reboot it. Found it. Not a bug, it's a feature. Okay. So let's do Gauss's law for a point charge. We're gonna start really simple, not because we need to know the answer for what the electric field of a point charge is, we already know that answer, but to show you how we approach finding electric fields using Gauss's law. So, a point charge, just a single charge in space, right? Okay. We want to find the electric field around this point charge. Gauss's law tells us that the electric flux is going to be equal to some amount of charge that's enclosed by a Gaussian surface divided by this permittivity of free space number. Okay. Who's in charge of the Gaussian surface? The universe or you? Me. I'm in charge. This is my thing, right? It's an imaginary surface that I'm going to draw around this point charge. And what you want to do is take advantage of what you already know. What do we know about the electric field of a point charge? Like, what does it look like? How is it shaped? It's like a bad hair day, right? Okay? It's that just pushing out of, yesterday. It wasn't bad hair day, it was a good hair day. Cynthia and Natalie, right? Okay? With their hair sticking out from the Van de Graaff generator, right? Okay? We can draw, they're like a point charge, right? And we draw a Gaussian surface. But we want to, as much as we can, we want that dot product right there to be simple. Like, what's the definition of a dot product all by itself? Like, if you have A dot B, what's one way to write that down? AB cosine theta, right? And so the simplest calculation to do is when the angle is what? What angle can we put in there to make this simple? 0. Cosine of 0 is 1, right? Okay, and then we just have to multiply the magnitudes together. So that's kind of what we want to do. To avoid doing the integral on the left-hand side, we're going to be clever about the direction the electric field is pointing, we think, and the area vector that we have. Mr. Balogh, area vector, I'm still struggling with that one. But now, like, how do I know what shape or size? Go with the flow. I wait all semester. Which way is the flow? Outwards, okay? Is there a three-dimensional surface that has area oriented outwards radially in all directions? It's a sphere. Good job, right? You took that idea of a sphere and you realized that the area vectors have to be what? Perpendicular to the surface at all points, right? Okay? And so the area of a sphere, if I go and I take my Gaussian surface and I can't draw a sphere to save my life, so I'll just draw a dotted line that looks like a circle, right? These area vectors are all pointing outwards, away from the center of that sphere. And that's for every sphere. Now you know. And knowing is how you know stuff, right? So if you've got something that has this spherical outwards flow to it, or even that's just your guess, try a sphere. It's great. Okay, so what does that mean this integral becomes? Well, we're going to integrate all of the area of that sphere, right? The electric field, we know, points in the same direction as the area vector, so it's like the dot product goes away, okay? And it's EDA, right? But then we're going to integrate over the entire surface area of a sphere. What's the surface area of a sphere? Is the electric field constant over that surface? Is its value and direction the same everywhere over that surface? Yes. So the electric field comes out. We have the integral of dA over the entire area. What's the surface area of a sphere? You've come this far, don't biff it. Four pi r squared, where r is the radius of this Gaussian surface, okay? And then, yeah, that's good. And then that's going to be equal to what? Q enclosed. Let's just say that's Q divided by epsilon naught. I now solve for my electric field. That's Q over 4 pi epsilon naught times r squared. And what's 1 over 4 pi epsilon naught? Okay. It did require us to have a conceptual picture, framework in our heads for what electric field is doing, to be able to avoid doing that integral. I did an integral, but didn't really do an integral, right? I thought my way through it. I thought my way through like thinking about what it was saying. And this is the pattern that you want to establish. You look at that integral, you go, okay, how do I avoid doing that integral? I'm going to find the surface area of a shape that I know. And that shape is going to be a sphere, a cylinder, or a box. Because what's the surface area of a sphere? 4 pi r squared. What's the surface area of a cylinder minus the ends?
Minus the ears.
Don't worry about the surface area of the ends. 2 pi r times h, or L. Right? Okay? Yeah, it's all right. We'll get there. And what's the surface area of a box? Length times width times 6 if you had to go all the way around. But often you can ignore some of those sides. We'll talk about why in a second. Okay? But really, that's every integral at the physics 4B level that you have to do on the left-hand side. Okay? I don't know about you, but that looks elegant to me. Compare and contrast. Dare I do this? Compare and contrast with I didn't write it down there. I mean something like this. That's a mess. And it was a lot worse, wasn't it? When we did it? On other pages, okay? I'm not going to take time to go find them, right? But, I mean, wow. And granted, the one I just showed you was more complex, but we'll get there. We're taking baby steps. We'll get there. Okay? All right. So what's next? Line of charge. That's great. Remember our rods?
It's not showing it.
Supposed to. Do I have to restart again? So many technical difficulties. See, I knew I shouldn't have. Close that one down and redo it. Sometimes the Wi-Fi gets really weird in here. Causes problems. It's weird everywhere. There we go. Okay. Whee! Okay. Line of charge. Remember? Okay. Do you remember the perpendicular bisector? Do you remember the charge along an axis? Find the electric field at the origin. Remember all those things? Right? Let's do it. I want to find, and we'll just kind of say that this rod is infinitely long in both directions. I'm only drawing a portion of it, okay? And before we had, if I wanted to find the electric field, say at this point, right? I'll say it's a distance r from the thingy. Gotta find don't write this down. Had to find a section, and I had to do the r vector, and then and then integrate, and right. Okay, and it kind of got really scary. Gauss's law method. I don't do the integral. I do see, and I might. I've been writing capital Q. I do the integral I don't see. Well, luckily, right now, I don't think I have to integrate, because if I just put charge on this thing, then it's just, that's the amount of charge. Anyway, but let's see what happens, okay? It's got charge on it. It has a length, L, we'll call it. What do I know about the electric field of this thing, right? We've dumped this positive charge on it. It's a conductor, so it just spreads out. It could be an insulator, it doesn't matter. going? When did it do that? Right away? You saw it work, right?
Oh, stop recording.
No, it's this program right here that's causing. I think this one has lost its mind. Are we good now? Yeah? Okay. So, I've got charge spread along it. I got L. What does the electric field look like? Like what should the electric field be doing around this rod? Kind of going out, right? It's like a bunch of positive point charges all next to each other, right? That all are having bad hair days. But are the electric field lines allowed to tangle and cross? No. So what's going to happen is they'll all be pointing like away like this. Something like that, right? Okay. So they've got this out, and of course it's in 3 dimensions, right? So like flowing outwards, okay? And I need a shape. I need an imaginary shape that allows me to capture the essence of this field. That ideally has an area vector that points in the same direction as that electric field. It's the cylinder now. If I take and I wrap this is going to be terrible. If I wrap a cylinder around this rod, okay, right? Why can I ignore the ends? Why don't the ends matter? What direction is the electric field pointed compared to the area vector on the ends? 90 degrees, right? And what's the dot product between two things that are 90? There's no flux through the end cap. So that means the only flux I'm going to have is through the toilet paper roll part. Okay? So that means that this integral, again, the electric field is a constant, and my area is going to be 2 pi r times L. I can use capital, I guess. L is the length of my cylinder. I should have done that in blue.
Is the cylinder like, are we just wrapping around this certain area, or is it going to infinity?
The cylinder does not go to infinity. Yeah, the cylinder has length out. The wire is going infinitely far. I want to avoid edge effects. So that's why we're doing that. Okay. Oh dear. Oh dear. So Q has been spread out on this rod. And I'm only looking like, I don't have the whole rod inside of my Gaussian surface. I just have a portion of the rod inside my Gaussian surface. How do I figure out how much charge is inside there? You don't have to integrate because if it's constant. Don't I already have a way to figure out how much charge is inside something that's straight? Yeah, the answer is yes. I do have a way to do that. So that means that my charge enclosed is going to be lambda, which is the same no matter where I am on that rod, times the length of my Gaussian surface that I have. Now, I am getting a little bit nervous because a Gaussian surface is an imaginary friend. It doesn't exist. And so I really don't want my answer to depend on that Gaussian surface if I can avoid it. Now, back when we did the sphere, yes, it depended on the radius, but that was okay because we know the electric field varies as we go out, right? But does the electric field vary as we go along the length of this wire? Not at all. The only way it varies is in my r direction, radially away, right? But I've got L's everywhere in this equation. In other words, I've sort of hardwired this thing to my Gaussian surface. The Gaussian surface is finite, but my wire is infinite. So that's kind of bad. But we're okay here, aren't we? It cancels out on both sides. So if you've got a Gaussian surface and you've got parts of it that seem to be sticking around, there's probably a way for those parts to cancel out. Okay? We know there's no variance in this electric field along the length of the wire. It only varies moving away from the wire. And so we want that to cancel out. And in fact, just a little bit of patience, and it will. The electric field of an infinite charged rod or wire or insulator is going to be lambda over 2 pi r epsilon. Which is, I believe, the answer that we got when we integrated the infinite wire along the perpendicular bisector and said that it was infinite, right, in both ways. It's simplified down to this. Sammy.
This is not a vector anymore.
This is the magnitude of the electric field. What do we know about the direction of this electric field points? It's outwards, right? So yeah, we're finding, Gauss's law helps us to find the magnitude of the electric field, right? What price are we paying for this? Imagination, concept, idea. Mathematically, is anything I've written on the page hard? It's understanding what's going on behind the mathematics where you do the heavy lifting when it comes to Gauss's law. We're going to keep applying this on Wednesday, but let me leave you with one last story. I was in graduate school. We were solving a problem. Now, if you want to make a physics graduate student cry, just walk up to them and say, Jackson. That's all you got to say. Jackson. It's the name of an author for a book that's called Electrodynamics. It is quite possibly the worst textbook ever written. I was there when Amazon was born. We went on Amazon to see if this had been reviewed. It had one review, brand new Amazon, right? One review for this textbook, and the review said, would it prefer a poke in the eye with a sharp stick? Says it all. We had this problem. It was a wire, a coaxial wire, still remember all these problems, that was half filled with insulator, and the other half was empty. Find the electric field everywhere inside of this coaxial wire. Jackson is a textbook where you work on a single problem for days. Literally 3 or 4 days, 8 hours a day, in between your other classes, and in between working in the lab and TAing or whatever, okay? You worked and you worked. We would fill chalkboards and whiteboards full, and we would kind of tag team, and one person would have the 12 midnight to 2 a.m. shift, and something like you're sleeping on the couch, you wake up, and you're doing more math, and it wouldn't stop. It was awful. We had this problem. We knew we had at least 8 to 16 hours of work ahead of ourselves. We started work on it. 40 minutes in, we're getting nowhere. Tom, who was the smart one among us, there's about 5 of us all working together. Tom, who was absolutely brilliant, had been kind of quiet. He usually did all the heavy lifting when it came to the math, because I was good at concept, Tom was good at math, and the others were good at other things. Tom had been really quiet, and he had just was sitting there. Just like that, grabbing his chin. And all of a sudden, his eyebrows just climbed up his forehead. And he said, oh my gosh. And we're like, wait, Tom's about to speak. Everybody shut up. And he looked at it, he's like, you can use Gauss's law. We hadn't heard of Gauss's law, in decades. Graduate school just puts years on you, right? Okay? And it's like, wait, Gauss's law, what Gauss? I remember, what was Gauss? Oh, that was that thing we learned back when we were innocent. And he's like, yeah, I think we can use Gauss's law. And he stood up, and he used Gauss's law. He solved the problem in about 4 minutes. And we're like, there's no way this can be right. There's no way. We marched down to the teacher's office, and we're like, look at what Tom did. And so Tom explained, the teacher went, that can't be right. And then Tom went on for the next 50 minutes to prove to him mathematically that it was totally consistent. We got lost about 2 minutes in. Okay? And the teacher was sitting there going, no, that can't, no. And finally the teacher threw his hands up in the air and said, you know what? I'll do it. I'll do it the way Jackson says to do it, and then we'll compare answers. We're like, okay, when are you going to be done? He's like, it'll take me about 6 hours. Come back tomorrow. So we did. The answers were identical. Gauss's law is responsible for me being able to go home and see my wife that day. I hadn't seen her all semester, right? Okay. But because of Gauss's law, we had a date. It's amazing. I love Gauss's law. I will see you on, not Monday, right? Tuesday. Next Tuesday. Oh my gosh. Be good. Don't get hurt. Come back to me in one piece.